Dear students, in today's video, we will calculate the pH of weak acids. Let me demonstrate this by solving this problem that you can see on your screen. Find the pH of 0.1 molar CH3COOH, which has Ka value 1.8 into 10 to the power minus 5. Let's look at the problem by taking this general acid over here, and we can also write acetic acid in this form as well. A weak acid dissociates into H positive ion and A negative ion in solution. And if you take the example of an actual acid like CH3COOH, it could be written like this. And in the form of an equilibrium expression, we can write it the concentration of H positive ion multiplied with A negative ion divided by the concentration of undissociated acid. It must be noted that weak acids hardly dissociates in water. And if we take the example of CH3COOH, it only dissolves up to 3% in water. What happens initially? An acid dissociates into H positive and A negative ion, but as the number of H positive and A negative ion builds up in the solution, they recombine to give us undissociated acid. There comes a moment when the dissociation of HA into H positive and A negative ion and recombination of H positive and A negative ion becomes equal. And that particular moment is called equilibrium. Let's solve this problem using ICE method. I mean initial concentration, C mean change in concentration, and E mean equilibrium concentration. Initial concentration, as we have been given, is 0.1 molar. If you look at this expression, this shows that 1 mole of HA dissociates to give us 1 mole of H positive ion and 1 mole of A negative ion. Initially, we have 0.1 mole HA. Since the dissociation hasn't happened, so we won't have any H positive and A negative ion in solution at the start of the reaction. Change in concentration. 1 mole of HA gives us 1 mole of H positive ion and 1 mole of A negative ion. This means that if we have X mole of HA, this would give us X mole of H positive ion and X mole of A negative ion. So we can write change in concentration. Since 1 mole of HA or X mole of HA are dissociating now, we can write minus X. Minus means the concentration of HA is decreasing. And for H positive ion, we can write X, and similarly for A negative ion, we can again represent it with X. Equilibrium concentration. We can write equilibrium concentration as 0.1 minus X, as this is the amount of acid that has been dissociated into H positive and A negative ion, which means we will have to subtract it from the initial concentration. So initial concentration are 0.1 and minus X is the concentration or the amount of the acid that has been dissociated. So let's put in these concentration into our equilibrium expression. So here we are. In place of H positive and A negative ion, we'll submit these equilibrium concentration, and similarly for HA, we'll write 0.1 minus X in the denominator. And 1.8 into 10 to the power minus 5 is the Ka value. Now right from here, we can solve this problem using two methods. One is a longer method and the other is a shorter method. I will stick to shorter method for this particular example. The longer method requires quadratic equation to be used to solve for X, while shorter method requires that we must make some sort of assumptions or approximations to solve this problem. As I have just shown you that the acetic acid is so weak an acid that just 3% of it gets dissociated in water. This means that with regard to 0.1, X is too much less. So we can ignore the X in the denominator. And the expression would become like this. X multiplied with X squared, 0.1. And now we can multiply this with this left-hand part. And here we are. And this would become 1.8 into 10 to the power minus 6. Let's take the square root of this number. And the value of X would come out to be 1.34 into 10 to the power minus 3. And you know what is X? X is H positive ion, and similarly it is A negative ion. Since we are finding the pH of weak acid, so we'll look at H positive ion concentration at equilibrium. Now we know the pH is equal to negative log of H positive ion. So these are H positive ion. Let's put this into this expression and solve it, and the pH would be 2.87. So the pH of this 0.1 molar CH3COOH solution is 2.87. It must be noted that when you are making an assumption over here, just divide the initial concentration by equilibrium concentration. If this comes out to be too much than 100, this means x is very, very small. Ignore the x. But if it comes out to be less than 100, then go for quadratic equation. You can verify it. Equilibrium concentration divided by initial concentration. Equilibrium concentration are these one. Initial concentration is 0.1 and x is less than 0.5%, which means, as I've told you, acetic acid is dissociated only 3% in solution. And this is what you can verify it over here as well. I hope you have found this tutorial useful. Please leave a like, subscribe, and thanks for watching.